In our previous video, we talked about the scientific method, which relies on experimentation. So when we are doing those experiments, what does the data look like? When we are doing a scientific measurement, we collect data, and that data can be either in the form of qualitative or quantitative. Qualitative observations are those that have a non-numerical component. Typically, they are answering questions like, did a solid form? What color is the flame, or possibly what color is the solid? They are typically descriptive in nature, describing your observation. The key thing is that a qualitative observation does not have a numerical value. Quantitative data, on the other hand, is quantifiable. It has a numerical value associated with it. Typically, we are using some sort of glassware, balances, instrumentation to generate empirical data that has some form of a numerical value and standardized units. There are two primary systems of units that are still being used. There is the English or imperial system, the one that is used in the United States, which has measurements like feet, inches, gallons, cups, and so forth. And then there is the metric system, or the Système International, SI, which is French for International System of Units. This is the one that most other countries use, as well as what we will be using this semester. It is the primary system that gets used in scientific observations. So once we have collected our data, there are a bunch of different ways that they can be related to each other. And we talk about this in terms of the different types of variables. There are 4 different types of variables in an experiment. There are independent variables. These are ones that do not change as the result of another variable. Examples of these are time and initial concentration. Initial concentration, once you start an experiment, you can't change your starting values. In a mathematical representation, such as y equals mx plus b, this would be your x value. Right? Typically, your independent variable is your x. Y is dependent on what x does. This brings us to dependent variables. These are numerical values that change based on another parameter, and that other parameter are often independent variables. Examples of these could be something like concentration, not initial concentration, but current concentration. In terms of our earlier example of a linear equation, y equals mx plus b, the dependent variable would be your y. It is dependent on what your x value is as to what its actual numerical value is going to be. We have controlled variables. These could be either independent or dependent variables. These are ones in an experiment which we keep constant. So some particular type of variable that we're able to tightly control. Examples of these would be temperature, time between samplings. It could also be initial concentration. Things that we are able to keep constant are called controlled variables. Then we have codependent variables. These are ones in which you have 2 or more variables that affect each other. Later on, when we are studying gases, we will be talking about the ideal gas equation, which is PV equals nRT. So pressure times volume is equal to the number of atoms you're working with times a constant times temperature. In the case of your pressure and volume, or temperature and number of atoms, these are all codependent variables. When you change one, it changes the others. So in terms of mathematics, you could have 5 is equal to a plus b. If we change b, then a changes in response to that. We could also change a, which would cause b to change. So codependent variables are ones in which you can change either variable and the other one changes in response. Now, the values that you have, your experimental results themselves can show relationships between your various parameters. So between your various types of variables. There could either be a correlation between your 2 variables. The change in one parameter appears to affect another. There is causation, which is a much stronger or higher bar in which one value does in fact change the other, or they could be unrelated. One value appears to have no effect on the other. A key thing here that is often confused is the relationship between correlation and causation. Correlation is different from causation. If you're reading in a lot of current literature or news reports, they often confuse these two. So you might hear something like consuming red wine leads to longer life expectancy. That is a correlation. It does not prove that imbibing red wine itself actually causes someone to live longer. It could be instead that if you have the financial means to drink red wine every day, then you're probably eating a better quality of food, and it is that higher quality of food that is actually causing you to live longer, right? So correlation does not necessarily mean causation. It just means that the two parameters appear to be related to each other, not that they are related to each other. Causation, by changing one, it in fact causes the change in another. Correlation is as one changes, the other one appears to change with it.